Shijin from Princeton Computer Science will be giving the talk next week. And since I'm eager to hear what's going to happen, I'm going to introduce you now, even though it's a minute early. Okay, so Emily, first, if you haven't met her, she just arrived here at Rutgers this year in the computer science department, and she's going to talk to us about a survey on AI for proof assistance.
Yeah, thank you for the introduction. This talk is by no means a comprehensive survey, I would say. It does kind of brush over many details just to kind of provide a little bit of breadth, but also kind of focus on things that I felt like, were kind of formative in the development of this sort of research direction. So hopefully coming away from the talk, you kind of get a sense of like the general state of this field and how it has progressed over time. Maybe it will inspire you to look up some of the details in some of the works that are mentioned here. Maybe it'll then give you ideas to then pursue your own research in this area, potentially. Yeah, so just a little bit of orienting, because I don't really know who's in my audience. Oh, is this not? That's a problem if I can't go to the next slide. 1 second. Okay, yeah. So yeah, just a little bit of orienting because I don't know who's in my audience, and also in the Zoom audience, there might be just some people who are just computer science, just math. So when I talk about informal theorem proving, it's all in sort of natural language, right? We have a natural language statement or conjecture, and then you have a pen and paper proof. So you can kind of reason about the proof and be like, yeah, I think it's right in the end, but you've not formally checked it. Where formally checking something is doing it programmatically, where you can define, let's say, the natural numbers inductively and define addition, and then state your theorem in a formal language and write a programmatic proof that is then machine checked for correctness. And so this is all done potentially in tools called proof assistance. So a lot of you are probably familiar with Lean, which Alex spoke about 2 weeks ago in the seminar. I kind of walked you through how to use Lean and how to use it with AI. But there's other proof assistants, So one called Coq, or has now been renamed to Rock, and another called Isabel. And they allow you to perform this interactive theorem proving, where you state a theorem, prove it, and then this proof is machine checked. So how do these proof assistants work? Kind of seems like magic. I won't go into details here because you can probably have like a whole other talk on that. So in the interest of time, I'll say that they typically have some logical or type theory basis, and proving a theorem in them amounts to applying rules from a formal system to transform the goal, which the goal first starts off as the theorem itself, until it becomes something that's trivial. So one could try to prove the theorem directly in the proof assistant logic, but that's a very unforgiving task. So like writing something called a proof term, you have to be completely precise. Well, instead, you can use things called tactics. So these high-level commands, essentially, that abstract away some things for you. And so a tactic could be example like induct on n, or reflexivity, which is saying that, oh, the left and right hand side are the same, so yeah, we're good. So you can use these high-level tactics that these the improvers provide to guide the process.
Like people code in Python, not in machine language.
Exactly, like you're not writing assembly code. Yeah. Yeah, it's a great analogy. Yeah. Why would somebody want to use a proof assistant? So formalizing math is definitely something that this seminar focuses on, and this is like the domain for it. But my personal domain of choice has actually been in software verification. where you can say, hey, I have some code. So here it's like a reverse function on lists. And I want to prove something about this code that, I can append things and, reverse will still work as I hope it does. And then write proofs. And so that makes it so in software verification, you can hopefully, by going about this process, get to more bug-free code. Because you're more sure what's happening there. But for the rest of this talk, I'll focus on formal math. And so formal mathematics, the reason maybe you'd want to go through any sort of arduous process is that maybe it can help provide some rigor. And one of the kind of first, I would say, experiments in this direction that like really kind of caught people's eyes was this thing called the liquid tensor experiment. And so this is where somebody named Schultz presented a challenge online to formalize a theorem about condensed real vector spaces, and somebody else, Comelin and his team, rose to the challenge. They're like, yeah, we could do this. And then they did it. Maybe it took like a year or two, I think, but I don't know if they were using AI actually to do that. They were not. So
This was before GPT-3.
yeah. So pretty impressive that they were able to do it at all. And at this point, a lot of undergraduate mathematics has actually been formalized in Lean in the library called MathLib, which last seminar, Alex was kind of retrieving all these premises from, essentially, to apply in like the proofs that he was working on. And so having like this good sort of a formal foundation will allow for future formalizations of complex theorems about complex objects. And so the process itself that like a human would go through in writing a proof assistant wouldn't really look like an iPhone conversation like this, but it would be a back and forth that they would have where they would start by stating, some theorem. The proof assistant would tell them like, this is the current goal that you're working on. The user would provide a tactic. It would say, okay, now this, here are the intro n. So now n is in their local context of assumptions. Then they say, okay, let's induct on n. And now the state says, okay, there's two goals you have to work on, the base case and the inductive case. And you would kind of keep iterating on each until there are no more goals left. And in Coq itself, you actually just write QED at the end. So it's kind of satisfying. So this could be a really arduous process, as you can imagine, taking years to do, many lines of code. Software proofs especially, they can be like super long because there are a lot of different case analysis and things. So how would we overcome these sort of difficulties? Well, it'd be really great to automate things, right? And so if you think about maybe the software verification process or the math proving process, it's this big kind of pipeline of where different aspects of automation could really help. But the vast majority of the existing work on this topic of automating things in proof assistance has been about automating the proof writing itself. And so a lot of assumptions are made in a lot of papers on this topic, where essentially they assume that all this beginning process has already happened. You've have somebody that has formalized all these statements into the theorem prover language, and then and even all the helper lemmas that you would need to prove along the way. And at this point, the task would be just try and synthesize a proof, given all this wealth of contextual information that you have. So it's a pretty sanitized task in that way. But still, it's not something that's able to just be completely 100% automated. So the first tools in this space were not using AI machine learning. They're actually these sort of tools that use constraint solvers. And they're at times like integrated fully into these proof assistant tools. So, and there's even entire languages like Daphne, for example, that support this. And so tools like hammers, for example, they call out to SMT solvers when attempting to try and like hammer out a proof. And so how they do that is they try and translate the current obligation into the logic of the SMT solver. Then the SMT solver, then, you know, even multiple SMT solvers try and like solve the obligation. If they're able to then, you know, construct a proof, then translate the logic back into the logic of the proof assistant. But there are some core limitations in being able to use them, namely, they can't perform induction. So, but I mean, you can still use them in an induction proof where maybe you start by inducting on something and then you solve the base case with the hammer and even sometimes the inductive case with the hammer. They also struggle with higher order logic. So they're really good at first order logic. So it's kind of like their bread and butter. So while they are powerful at times, so for example, about like 1/4 of a benchmark in Coq can be solved by Coq hammer alone. I'm not sure what it's like on lean benchmarks. People don't really evaluate lean hammer.
I wish we had something as powerful as Cock Hammer.
Yeah, sledgehammer is actually probably like the most powerful, and that's the one for Isabel. And yeah, I think lean hammer is actually fairly new. This actually came as a surprise to me a couple weeks ago that it actually existed. And there's other automation tactics. Grind, yeah. Yeah, so they're all like using these different automation.
None of them are good enough.
Yeah.
For undergraduate real analysis.
Yeah, but they could potentially be like complementary to AI techniques, be used within an AI technique to kind of dispatch some of the obligations. But yes, overall their power is limited. So that's
Is that what Leo DeMora created before he made Lean?
I think so, yeah. So it's a SMT solver. Yeah. So there's other ones like eProver, Vampire, CVC4, is that what it's called? CVC5. Well, first came 4.
Is Vectorsky different from CVC5? Is there something Vectorsky?
I'm not familiar with that actually. Yeah.
We tried to use it because we were trying to solve questions of high order logic, but it wasn't very efficient.
Classic. Yeah, so that's kind of like, okay, so all these automation tools, maybe they're not good enough. So maybe AI can be our answer and overcome some of these limitations and help with automating the process where if you have a proof, like ask AI to just generate it. And we can kind of see that some of these ML-based tools for Coq can prove over 1/3 of that sort of benchmark. And on some of these lean benchmarks even, like they're fully saturated by some of these AI tools. It's a little unclear how to interpret some of these results. Is it that the problems in this lean benchmark, for example, on Math Olympiad problems, like is now too easy for AI tools? Is it that AI tools have maybe seen these problems before, sort of thing? So it's not clear, and so benchmarks are not always like the best indicator of where the AI is at.
Is that because Coq and lean are divergent enough that you can't have the same set of benchmarks for both of them?
So it's, I guess, to make a benchmark across languages, you need somebody to take the time, essentially, to write those formal statements in that other language. So not everybody wants to take that time. So the benchmark I was referring to with this lean one, I think it actually has a Coq version. It definitely has an Isabel version. So that's like a cross-language benchmark. But essentially, like the benchmarks themselves are maybe more motivated by the community that is using these proof assistants. So this Coq benchmark, for example, is mostly software verification problems, while the ones in Lean are basically all math problems. Yeah.
I think there is a
Oh.
translation from an auto translator from Isabel to Lean, but only on the level of the terms.
hmm
So it's like assembly translation, and it's hard, it's god awful, and you know, can't use it for math, for example. The proofs that it gives it.
Yeah, right. Like if you do some of these translations, then like the ending result, is it like how usable is it? Like how readable is it? Things like that.
So
I-
I'm
the-
not very familiar with interactive circuit proofers, but if I understand correctly, like Lean and Coq are both based on construction, calculus constructions, right? So
Practice and construction.
yeah, so what makes like Lean more, seems like it's more popular with applications, right?
I think it's really mostly a community effort. It's just like, they're all like, okay, let's focus on this one. Let's make a big library of math. Let's go all in on this. I think then now people are really doing a lot to maintain the library, and try and even now like create AI tools for it. So I think it's mostly just the community around it is what's really kind of pushing it forward in that way. Coq, though, like it's not used by a lot of people, like a lot of people in France, because that's where they made it. And yeah, I'd say like building a tool, like an AI tool to really interact with Coq, it can be a really big headache. Um, so yeah, I'd say, yeah.
Are these standard-based tools streaming like language models or like some other AI?
Well, I'll get into that, but yes, also language models.
But usually, in the alarm, when you see like 100% of nearly 100% of some benchmark has been solved by because often it has got to to a front that there's a lot of data contamination.
Yeah, for sure. Yeah. So then there's also efforts by people to try and like make new benchmarks that are maybe on more recent projects that haven't been uploaded to GitHub or somewhere, or the Google, for example, they evaluate Gemini and their alpha proof tools on like the coming years or this year's IMO challenge problems. So then it's like, okay, those haven't been seen before necessarily in this exact way. So this is now a much smaller benchmark for how well their intelligence is doing. Yeah, so
I
that's
have a
why
question.
I always am really dubious of a paper that's like, we get 98% on mini F2F, which is this kind of benchmark, or like we fully saturated mini F2F. It's like, okay, what does that mean? Like, how do I know that it hasn't been contaminated? You don't. Yeah.
Hi, I have a question.
Um,
I'm
but
on
yes,
the
and there
one-
also are people that
She can't hear
are
me.
work in the past that's not on these large language models. So then there's not as much there's not that risk, right, of the contamination.
The proof actually worked. Is it proof that an AI generated?
It's not an AI generated proof, actually. Yeah. I maybe took this from MathLib.
Okay.
Yeah. Oh.
Contamination is not necessarily a bad thing. I mean, it depends what you want the AI to do. If you want the AI to come up with brand new proofs for every problem, then it's a bad thing. If you want the AI to be a teaching tool, then it doesn't matter how it plugged in and how.
Exactly, yeah. But then the benchmarks themselves, like what is the purpose of them? That becomes the question. Are they actually telling us things? Well, I think there's like a chat. I didn't even realize.
Yeah, can you
I'll
hear
get to
me?
chat things at the end, or yeah. Okay, so yeah, I guess I'll
Oh, looks like
continue.
you can't hear me. Okay.
Cursor. Make sure I click on this. Okay. But then kind of like the reason why a lot of AI researchers are interested in this space is because theorem proving can be kind of important for AI. So already been brought up is large language models. So they have, incredible reasoning abilities on like a wide range of tasks, but they're notoriously really difficult to kind of verify their outputs, right? Like determine whether, or automatically or easily, whether they're doing what they say they're doing. So you can generate code and they'll produce good answers, but they also can sometimes produce convincing wrong answers. And so it's difficult to kind of trust LLM output. But, oh yeah,
Actually, there's a question in chat, I don't know if you want to ask it, but.
yeah, you can present the question. Yeah, it's just hard for me to monitor the chat, so if you want it,
So,
yeah.
Slides back. Yeah, before this. Yeah, so the question is, are these steps outlined in italics generated by LLM? So he's talking about these.
Are these steps outlined by what?
Outlined in like italics generated in LLM. So I think he's asking if this proof is an LLM generated.
You said already.
Yeah, so this is not, yeah,
This is-
yeah. Was there another question from the chat? Okay. Yeah, that's a good question because it was already asked in the room. Yeah, so nice. Yeah, so the proof assistant, at least when you have like a theorem that you know to already be true or something, or it's been formalized in a way that you know, have assurance of. When you generate the proof itself, that generation, proof assistant really acts as like an oracle, right? And so then if you have LLMs generating proofs, that makes it so theorem proving kind of becomes this powerful domain in which you can evaluate LLM reasoning capabilities, and maybe say something about the LLM's capability overall across domains, but it's really acting as kind of this playground for LLM reasoning.
And the point is, there's this ansatz, which I don't know why it's, I mean, I can imagine why, that if you can get your LLM to solve math problems, then you can get it to do anything. Right? That seems to be.
Yeah, it seems to be
why
like.
They get interested in theorem.
Yeah, so it's like, I guess it's like an easy way for them to verify it, and so then.
That doesn't, if it can prove theorems, doesn't mean you should trust its output on an essay or something.
Yeah, but this is just what the AI community is kind of like now focused on, I would say. Whether they should be focused on that is it's
There's
not.
no theorem that says that that's.
Yeah.
How it's gonna go.
Exactly, yeah.
As
But.
long as they keep helping us, we don't mind.
Right, yeah, so you should take the help where you can get it, right?
Exactly.
Yeah. Yeah, so there are like more natural language math benchmarks. But then it's like, oh, well, they don't have the check marks, so let's switch to this, right?
So that the answer is a number, a whole number.
Yeah, yes. Yeah.
Which we're trying to do it even for history, which is fact space, there is no notion of absolute truth.
Even physics. This doesn't help physics. Any physics that this helps is mathematics, by definition.
That's right.
Yeah, I guess it's also like the case where people are thinking, oh, like let's see if my LLM can come up with like some new alien math, like something that's just, no humans have even thought of, right? And so if you can formalize that here and then have the LLM generate a proof of it, then it's like, oh, like it's doing things beyond human capabilities. But then you still need a human to kind of look at the thing it even formalized to begin with and say, is this even interesting, right? Like, so humans won't be obsolete, I would say, in all this. So don't worry. Yeah, so I guess for the rest of the talk, I won't really focus on the AI researchers' motivations. I'll focus on kind of trying to at least the good that they've done in trying to automate some of the proof assistant tasks. Yeah. So yeah, the way I've outlined this so far is kind of the fundamentals of AI for automated proof synthesis, kind of a really simple example of like a tool that kind of puts together these fundamentals. How we go beyond this, spoiler alert, with language models, what's the kind of, I'll present kind of all these different kind of strategies or model architectures, blah, blah, blah. What's even the best way to go about it? How do other parts of the proving process fit in? Like not just proof synthesis. And how does the human fit into this? So yeah, hopefully I can cover all this. We'll see. So existing work has built models that perform next tactic prediction, or even sometimes whole proof prediction to synthesize proofs. So typically these models in the past, even before LLMs, let's say, took the current state of the proof and maybe some contextual information and predicted the next likely step of the proof. But you can, ask for its top K predictions. So here, top 3 tactics, and then use the proof assistant to check the candidate proofs that are arising from applying those tactics. And so the proof assistant provides feedback in the form of an updated proof state or like even an error if you've done something wrong, and displays where, yeah, there are any errors. Sorry, I'm just reading my notes. So for the ones that do not result in an error or some sort of like repeated proof state, like if you're maybe just in like a loop, then you can, continue on those. So feed that like the partial proof back in to the model and continue on that partial proof. And if the state shows that there's no more goals to be proven, then you've successfully proven the theorem. So you can automate this within a search. So here's the start of, let's say, our search tree, where the nodes are the states that are resulting from tactic applications, and the arrows are the actual tactics that kind of bring you between different states. So in a meta-heuristic search, the model is biasing the search towards the likely next steps. So one could traverse this like search space in a depth first manner, breadth first manner, whatever, but we'll continue the search until one of the candidate proof scripts has no more goals left, and we can say that we're done. So the success of this approach greatly depends on how good the model is, right? Like the search space itself could be infinite. So you want to have something that's guiding the search efficiently. So one way to try and get a good model is to get high quality training data for it. So this training data can come in the form of other people's experiences with formally proving theorems. So the 3 proof assistants that I mentioned earlier, there's sort of publicly available data in the range of 100,000 to 300,000 theorems per proof assistant. And each have associated human written proof scripts. So like somebody took the time to formalize the proofs. However, as we kind of discussed earlier, like these different communities have different, these different theorem provers have different communities backing them. So that's why like there'll kind of be diversity of data, if you will, between each of these. So Lean, right, has all these math people, so a lot of excitement there from the math community, and a lot of the data is math proofs. So
35,000 theorems.
what's it now?
235,000.
235,000, yeah. Yeah, so I'll have a slide a little bit that I think I give the wrong number because it was from a year ago, that slide. So it's growing, yeah.
Number of years.
That's right.
Yes.
Lead class.
Yeah.
Do you know how much, like how most of this training happens? Is it reinforcement learning?
So the training I'm talking about right now in this, let's say I'm like, this is me 5 years ago. That's what I'm talking about. It's supervised learning. So you have some sort of input and output label. But later I'll mention reinforcement learning, which does help to improve the process and scale it all up. Yeah.
So do you expect like very good reinforcement learning to sort of take it all the way to like 90% or something like that? Like success on a difficult data set?
I think that's what people think.
Right.
Yeah. Whether I'm convinced, I'm not sure yet. Yeah. I guess I haven't seen it being used on my benchmarks yet to have that sort of convincingness, but just because there hasn't been the excitement around my benchmarks.
I mean, but I'll prove was training by reinforcement.
Exactly, yeah, yeah. And it was really impressive, right? But also for these IMO math problems. But I think some people have gotten access to alpha proof, and I think you might be one of those people. So there's other features of it that people really like, yeah. Yeah, so essentially, when you're looking to train a model in a supervised manner, you have some sort of input, and the output is like this target, right, that you want. So considering the MathLib library, let's say, is like a corpus for your training, and this is a kind of like a dummy theorem, let's say, that's in that library. A training example could be constructed from this. And so the example could be the input is the theorem and the output is the entire proof. But by doing it in this sort of coarse way, you're missing some sort of fine-grained information, such as the proof state. So typically in the past, researchers have extracted more fine-grained data by running the human written proof, looking at what the proof state is at every step, and then aligning the current state with the next tactic that the human tried.
Can I ask a really dumb question, something I never fully understood? Language models are next token prediction. So are we giving it, when we say input source, output source, is the context everything on the left-hand side, and then intro is the next token that it should learn, and then you add intro, and then A is the next token that it should learn, and then you add A to the context, and then B is that how they're trained? Like, how do you actually take this data and convert it into?
Yeah, so there's essentially it's a lot of these language models are, I guess you can imagine an encoder decoder language model, right? Where the encoder is taking in a sequence and the output is also a sequence. So you're asking it to given a sequence, output a sequence, and you can like stop generation at any time as well. So, but when you curate the data, you are curating it as this input output, and that's how it's seen. So like, given an input, the loss is then computed, like for like a decoder only model, let's say, it's computed over the output part of the sequence. I don't think I'm explaining this well, actually.
You have some hypothetical language model with some weights.
Yeah.
And you run that context in theorem add ABC, yada, yada. And then you see what the next token comes out to, and you want that.
Yes, and so these models are trained, okay, these models are trained with, at the end of this here, so at the end of like intros ABC, there'll be like an end of sequence token that it sees. So that'll tell the model like to stop generating almost. It could actually still generate beyond that, but you'll only, as a user, only take what's before that end of sequence token. So the models learn when to generate the end of sequence token. So if it's seen only examples of proof states and next tactics, it's learning when the tactic should end. Like, so no more, don't keep adding arguments to my tactic. If it's learned on theorems and whole proof prediction, it's learning, oh, this is when the proof is actually over. Don't generate a whole other proof for something else.
And so then the intermediate proof states just get added to context. Oh, here's by the way, what the model somehow learns in the model, it's learning the lean, how to keep track of goal states as it goes.
Well, that's not been actually validated whether it's actually doing that. I guess one can look at, let's say it's some language model that's producing chain of thought reasoning, and it might be itself like talking about the states, but it's essentially just all it's doing is relating the current proof state it's seeing as input to the model to past states that have been shown at training time. So trying to make these sort of analogies.
I think this kind of links out, like, when you're training these models for specifically Reggie's mappers, I guess like some people try to say like, oh, this model is understanding how to write proof. But it seems like it's mostly just understanding syntax, it's not learning semantics. So how do you know if it's actually understanding something semantic value rather than syntax?
Yeah, so I mean, one can like trivially generate syntactically correct lean code, but whether it actually compiles as a proof, that is where like the semantic aspect comes in, right? And so I guess you don't really know if it's if it's actually understanding the semantics. I think like still, that's why it's like it can be dubious if it's like already just seen other proofs and it's just kind of regurgitating those proofs again, right? Because it knows like what lean code looks like, and it can kind of
No, but it doesn't do semantics, and whenever you ask it a linguistic, one of these typical sentences. Like, the trophy didn't fit in the box because it was too small, is it the box or the trophy? It never gets the right, and I don't think it does any, isn't it proven isn't it obvious that the system does nothing related to semantics?
yeah, I guess in the realist way, yes, it's not doing anything related to semantics, but I guess we maybe as users looking at it feel like at times it is, right? And so sometimes we're not able to really attribute why it's getting some proofs. And so we now then think like it's because the reasoning ability of the model has gotten there.
So like I would think it could be like this, let's say you made this random wrapper on top of a link. That's completely different syntax, just maps, it's plain syntax. And you try to use LLM to generate using this new syntax. I would think it would not work, right?
Yeah,
Probably would not work well.
probably not. Yeah. It needs to see sufficient enough like data probably in your syntax to even come close to generating something that's reasonable.
We should try that experiment. There's a lean verbose, which is a wrapper on top of lean, which tries to make the lean proofs look more like natural language. So we can see how well an LLM could follow along.
Yeah.
There's like 1,000 lines of lean verbose in the universe, so couldn't have learned it from that, but maybe it could.
Yeah, so from my understanding, lean verbose is like controlled natural language associated with tactics, right?
Yeah.
So lean verbose, an LLM might be able to follow along okay with it because it is natural language, and so it's understanding that. But for arbitrary grammars or something,
Yeah, it's controlled by natural language, so it's actually you don't have a choice of what the next.
so you're saying that, okay, I guess you can use constrained decoding probably to force it in that way, but then that's not the LLM's capability, right? That's this sort of end thing you've put on the model, constraining its outputs, right? So yeah, I'm not like super optimistic at times about the reasoning abilities of LLMs, but um, yeah, some people are. Yeah, so I guess kind of just in the interest of time, yeah, so I guess a past kind of number was, can't even read what that is, 245,000. So this is from maybe like 2 years ago or something. That was the number that somebody extracted of, you know, proof state tactic pairs from only 116,000 theorems in MATLAB to create like a training corpus. And so, yeah, I'm not sure if I should just yeah, just I guess extra information that the model could want to see is like whatever premises are being used, right? Like how would it even know what nat add a soc is and nat add com are? Otherwise, it would just be hallucinating it if it wasn't given in the model's input. And so there are retrieval methods that can be used to retrieve, potential premises such as like definitions and lemmas that are considered useful for a proof state based on basically like the similarity of those to the proof state itself. And yeah, there's some research on to that end. And then there's other research on even like retrieving proof, so like proving examples themselves that are potentially helpful. And so I've been kind of a little not exact on what like the architecture is used at times, but in the past people have used recurrent neural networks. Other work has used tree LSTMs to encode kind of the underlying abstract syntax tree of the proof state. And even recent work in 2024 was using graph neural networks, since the relationship between different definitions and lemmas can be represented even as a graph. But most recently and obviously is the use of transformers, especially transformer-based pre-trained LLMs. So yeah, I just got tired of listing and I just said everything in 2025. So at this time, once we have a model, how do we want to search through the space if it's doing, let's say, next tactic prediction? So
What?
the search space can become kind
What
of
did you say?
unwieldy, and so naive, let's say breadth first search probably isn't going to do it. So instead, a really simple thing people have done is used best first search for prioritizing which nodes to explore in the tree. So we want to kind of try and choose the most promising unexplored state. So here, so we can kind of get the, for each prediction, we can get the log likelihood score from the model, and then sum along like a path that you're currently on to score the node, and then follow the nodes with like the best scores. So it's kind of understanding like the confidence of the model on that path.
Are you creating the entire tree? I don't know what that's first. Is it a score-based search or?
Yeah, so
Yeah.
it's just like imagining that the rest of the tree exists, like these are not predictions that maybe you've gotten yet. But if you're already on a path, or let's say you're at the node and then you get the next 3 predictions from that current state, you can score those predictions and then calculate what's the best, the back from like that path to then see which is the path you should kind of continue down.
Could you, I mean,
Yeah, I don't think this diagram is accurate. Yeah. Yeah, kind of just, I was confused as well when I was looking at my animations. Yeah. So yeah, you're right to be confused. But is there, you know, like a better, smarter search one can do besides following just the likelihood scores from the model? And so one can use reinforcement learning to kind of estimate the difficulty of a proof state. And so then guide the search towards more promising paths in that way. So if this is kind of a more true representation of like how a search would be going, looking at the log likelihoods of the model, and where like the colors here representing like the certainty of the model, the model might not ever, like the search might not find a proof. But if you try and actually score the states with some other model that's been, you know, kind of learned via reinforcement learning, it can kind of be telling you how many, from this particular state, how many steps it thinks is left in the proof. And so you want to follow states that have a score that's saying that fewer steps are left. You know, you're getting closer to the end of the proof, sort of thing. Yeah, so this can kind of at times be like an optimization where I think in practice it's really just found that like you maybe get shorter proofs. It's maybe not like super helpful though for finding more proofs. Yeah.
So this might be an ill-defined question, but this is something that so we can thought about. So I guess the idea of reinforcement learning is that these algorithms can do proof well. if they more closely align with how humans write proofs, so, instead of make it similar to humans. Is it clear that that's the best way to go about it? Maybe doing it in a non-human way would make it better or faster.
Yeah, so I've thought about that a lot. It's not clear whether, because I mean, here we only have that corpus that I was talking about, right? Where you can extract proofs from, and these serve as supervised examples. Just because a human did it that way doesn't mean that that's the only way or the most like logical way, or like that was like the way they did it when they first did it. Like that's like their actual, it represents their actual reasoning, right? So, for example, in MathLib, like that's a highly curated corpus where things are expected to be in a very particular way. Proofs are maintained and maybe tried to be more optimized or shortened. So somebody could have, on the first try, written a proof that went down like crazy paths, right? But it still got them to the answer in the end. They just didn't need to be proving some lemmas that they ended up proving. So it's not even that, maybe doing it human way is good, but I don't even think that the corpus that's being used right now is the actual human way. I don't know if that really answered your question.
Proofs are completely easy.
Yeah. Yeah, like induct on 11 or something was something that was in that. Like, what does that mean?
It's a reasoning token. It's
Maybe.
just wasting time,
Yeah.
just putting it back through the model a few more times.
Yeah.
It's learned that for some reason that helps it think. It's like when we take a walk. We don't know why it helps, but
That's an interesting way to think about it.
it's human prompting.
Yeah. Yeah, so I kind of mentioned some of the benchmarks already in Lean. The one I spoke about was Mini-F2F. There's also something called Putnam Bench, which is, I guess, meant to be harder. And then there's like the IMO challenge every year. So yeah. So just in the interest of time, I guess this was kind of a recording of somebody using this tool called Lean Copilot. Might be kind of hard to see. But yeah, you can try and use it to predict the next tactic given the state. It's very slow typing. And then it'll tell you, okay, these tactics actually, help or get you to a new state or something. Or finish the proof actually. So this one here is, okay, just try and search for the whole proof. And so I was doing what I said about like best first search with the next tactic prediction model. And yeah, so at times like these tools can be a little brittle where you'll ask for to search for something, it doesn't do it. So instead you can provide like a prefix, so like a partial proof that will then be inputted into the model. And then that then helps it to find the proof. So it didn't know where to start, but then you kind of gave it a helping hand.
Exact question mark would solve both of those.
Yeah.
Not a good example.
Yeah.
The exact question mark do the second one?
Yeah,
That's a bunch of lines.
no, it's a theorem in the library. S intersect T equals T intersect S, that's in the library.
Okay, well, that's cheating.
Well, that's what I mean by these.
But it wouldn't produce this proof.
It would not produce that proof, no, it would produce a one-line proof.
Yeah, so this was trained with like segmenting MathLib. So like it wasn't trained on some theorems in MathLib. So it doesn't know to just, yeah.
I find a lot of these Lean Copilot type tools to be very weak compared to existing tools that have no language component. And
Yeah.
even, weaker than the Claude type.
Yeah, so I think like that's kind of a big issue where you have people working on research in this area, and then they're kind of have given up on making any tools that are user facing
Useful to.
and useful to people. So you can still kind of like think about, oh, what's the best way to like approach this research problem, and have like a new technique in this space, but then it never gets in front of a user. And so, yeah, then nobody knows how it actually impacts them or not. While at times you can just use something like Claude Code and,
Or again, the built-in exact question mark just searches through the library and finds both of those theorems.
yeah,
The fact that Claude works is an instance of what is called the bitter lesson, which is
Yeah.
the saddest thing in the world, but it's very true, is that in practice, when you want to solve one of these AI problems, if you try to do something smart, or if you try to do something brute force with lots of resources, it's the second one that will work.
mhm. Yeah, it's a hard pill to swallow.
Bitter.
Yeah, so I'm just gonna kind of skip over some of this. Yeah, I kind of was talking about like, I was talking about next tactic prediction, but you could, with LLMs, right, just generate whole proofs, right? And just sample multiple times, scale up your inference. Some papers I see like are like, do it, pass at 8,000 or something. It's like, okay, wow, you had a lot of compute there to use. And so then checking at the end is just whether the proof is valid. But there's kind of like pros and cons to doing each, where with next tactic prediction, you're at every step you're having access to the proof state again to make your predictions on, while whole proof synthesis, you don't, right? Only when you kind of run the proof and see your error and see like where you've left off, do you get access to the state again. So
Token to stop at small steps.
it is in the sense that at every time you're reprocessing your input, right? So,
Supposed to one time just rate it and
yeah, because let's say you have like a whole wealth of contextual information that you're giving it, then you ask it to predict the next tactic, and you get the state, and you feed that back in, and also all your contextual information back in, and then so it's not as token efficient, especially on the input side.
on the other hand, if you're rating it 8,000 times.
Yeah, so yeah, so I don't think you win either way potentially, but I mean, maybe 8,000 times, that'll get you the answer. Well, maybe you'd never get it with next tactic prediction because you're not, using the high level reasoning abilities of LLMs and their ability to kind of zoom out on a proof. Yeah, so you can just fine tune LLMs to predict whole proofs, and then also fine tune them to even know how to correct their errors that come about when you check the proofs. But do we even need to fine tune models to do this? No, actually. So there's work on, even going from informal statements to formal proofs. And, you can prompt an LLM to try and just like do this auto formalization, and prompt it even with like natural language reasoning. So give it some natural language as input, or ask it to produce natural language reasoning. So chain of thought information as output. So do that informal proof. But there's one work that I thought was kind of cool, where it was giving these kind of in context examples of like, this is what a proof sketch should look like. So this is back in 2022, so kind of before the AI models that you know today. And then filled in the holes with calls to, let's say, hammers and whatnot. Yeah, so it's kind of like doing this sort of process in a different way. Yeah, and kind of getting the best of both worlds of symbolic and AI tools. So yeah, it's this draft sketch proof work. Yeah. But then you can also have like LLM agent approaches, where the LLM is just kind of on its own, interacting with the proof assistant. So you don't have to give it necessarily like in context examples that are formatted nicely or something. And so in this example here, it's the LLM agent is trying to decompose the current theorem into subgoals and then recurse on the subgoals. And if it finds proofs for the subgoals, then it composes a final proof in the end, sort of thing. You can also kind of prompt an LLM to be as an agent, trying to synthesize helper lemmas and things that then it can apply in the proof to try and get the end result. And so, yeah, this sort of like kind of leave the LLM to just do what it will and see if it comes up with a result in the end. So it's kind of like all these different ways of doing things, and it's not really clear which way is the best way. You can kind of have different models or different techniques kind of conducting their own proof searches and stuff. And in the end, it doesn't really matter which one you use because you have a proof assistant to kind of check it in the end. So it's at least if one of your approaches works, that's good enough, right? It's not as efficient though to kind of spin off all these different searches, but yeah, it's if the goal is just to prove your things, then you can do that. And the alpha geometry work kind of exhibited this in a way where they had kind of different independent proof searches and actually had like a sharing mechanism between them to kind of say like, oh, this proof search discovered some fact that this other one didn't, but I can share it between them, sort of thing. So kind of parallelizing all these thoughts. So yeah, I guess kind of want to get at like how other parts of the process fit in. So especially conjecturing. So where you can ask an LLM to just kind of try and conjecture theorems for you, given some definitions. And then you can try and prove them or use built-in counterexample checkers within proof assistants to tell you if there's, like something is not provable because there's a counterexample for it. Some of my work, I just wanted to plug, was using like a neurosymbolic conjecturing approach where you can have a theorem and instead of trying to conjecture that theorem, you can conjecture kind of like a template, so an abstraction of theorems that doesn't have function names or very like more normalized variable names. And then you can use symbolic tools to try and fill in the holes in that template. So it's more not asking the LLM to make the exact analogy that you want, but come close and sort of thing. And then you might want to be conjecturing not even just at the beginning of your process, right? You might want to be conjecturing within a proof, right, to help you get unstuck from something. And so there are some tools that do that. And then conjecturing itself doesn't have to be done separate from the proving process, right? Like conjecturing could actually help in terms of, yes, you might want to be conjecturing things while you're proving, but it also could help in the kind of training pipeline of models, right? So there was this one kind of cool tool from a couple of years ago, or I guess not a couple of years ago, 2024, we're in 2025, right? And they perform both conjecturing and proof search with actually a randomly initialized transformer, so doesn't know anything. And then they used kind of constrained decoding to make sure that the conjecture theorems were actually valid by construction, and then used like a proof search, like a Monte Carlo tree search to try and prove these conjectures, kind of generating more and more training data for the next iterations of the search. So yes, this is like a reinforcement learning approach. And was mentioned earlier was alpha proof, which has kind of this whole bank of informal problems, uses like a formalizer network. So let's just say like an LLM to just try and formalize them. Ones that can be formalized then can be constituted as like examples to be used and tried to prove within like the reinforcement learning solving network. Yeah, and so it did really well. It achieved silver medal status. And I think even now, like Gemini achieved like gold medal status or something. So only improving. And just kind of to concretize what like a basic reinforcement learning loop is. So you have an agent. So that's, let's say like an LLM here, and it takes actions based on some policy. And so the actions could be like try and generate whole proofs. And then it's interacting with the proof assistant and gets back states. So let's say it might tell you that there's goals remaining or that there are errors. And then you can then get a reward based on that. So you get like a positive reward of 1 if it's proven, or 0 otherwise. And this is actually like the reward that a lot of these recent work in using reinforcement learning is doing. So a pretty sparse reward in that way, right?
So when one does this whole proof attempt, right, okay, with some long sequence of lean commands, right? And it's quite possible that there are chunks in there that are coherent, even though the whole thing is that being exploited?
Yeah, so I think there is one work, I think Seed Prover, which came out a couple months ago, that said that they are using some of the aspects of the failed attempts in trying to, I guess, recover in like the next time that it tries with that one. Yeah.
Because you had earlier slide about the doing things in parallel, right? Where you can
Yeah.
share nuggets, right? So if you had something in the middle, I mean, that essentially becomes a lemma for nothing else, right?
Yeah. So I think they are using those like as like, oh, we weren't able to prove the whole thing, but this is some portion or some sub goal that we're able to prove. This is a good example to go off of. They also like, I think after some rounds of the loop, like they're filtering out problems that like shouldn't be seen again if they're too easy. So like if, there it wasn't very hard for the training to like, it wasn't very hard to prove, then they only focus on like the harder ones, sort of thing. Yeah, so I guess we're kind of at time, but kind of the gist is that these kind of recent reinforcement learning works are using reasoning models and collecting their reasoning traces throughout. So they have a lot of times like a separate formalizer that's trying to get formal statements to serve as, other training data that's maybe not like just human created training data that we already have. Sometimes though these statements, because they're formalized with this formalizer, are not necessarily guaranteed to be provable, so they also include at times the negation. So it allows it to be more exploratory in that way. And they exclude some of the easy problems that have, they say like a low proof rate. I don't really know what that means. That's why I couldn't really answer that for you. So they use also something called expert iteration, where as they're going about this process and collecting proofs that they're able to solve, that kind of serves as more training data on those collected samples. And they also then include a diverse amount of information, such as natural language, failed attempts, lemmas, error messages, stuff like that. Yeah, and then some also like are prompting their agent for specific strategies to be following. So one, like DeepSeek Prover, was prompting for trying to recursively decompose into subgoals and solve those subgoals. Well, the Seed Prover I mentioned, they want like, they call them lemma style proofs, where it prompts the model to just try and like construct all the intermediate lemmas that you want and then compose those into a final proof of the theorem. So there's some notable recent examples, and next week, will actually be on one of them. So you'll get kind of the juicy details on how that works. Yeah, so that'll be really exciting. Yeah, where does the human fit in? Not really. That's kind of the gist. I think we need kind of better tooling for all this. You know, kind of the general reasoning models of LLMs, they have really nice tooling that would be nice if some more specialized models could also have. Oh no. What happened? Okay. Yeah, so just some takeaways. Nothing, like not everything has been solved in this area. So, yeah, don't be shy about trying to start tackling something here. I think a big problem is efficiency, where if you say, like, I think there's been some recent results where it's like, oh, the Gemini proved some like really, really hard thing, and it was just running for like 2 weeks. That doesn't sound super efficient, not great for the environment. So trying to make maybe LLM reasoning more efficient in that way would be great. Yes, yes, and we did create these tools, so so yeah, we continue to wreak havoc. Yeah, I guess some resources. So yeah, I guess Lean Copilot isn't great, as Alex was kind of getting at, but at least it's something to kind of test out and try out, and see why it's not great. There's other tools in other languages. There's ways to kind of start using proof assistance. And there's an actual survey paper that's probably really out of date now, right? 2024 on on deep learning for theorem proving. But yeah, I guess I've gone way over. So yeah, thank you everyone.
Have covered the question